안녕하세요, and good morning, everyone. Unfortunately, my Korean is not very good, so for those of you who want the translation, you get a translator in front of you, which will translate my presentation in Korean. Now, I'm very excited to be here today, because I want to talk to you about how we're building into the future. Whoop. And that's my demo for later. That's my deck. How we're building in 2019. So I want to talk about new and modern application architectures. We're going to have a look at robotics. We're going to have a look at AI and machine learning and data analytics and how we do all of that in an AWS environment. But why are we talking about that? Well, the way we develop software has changed. First and foremost, everything has become data-centric. Data is the new value that we can derive out for our business, and when we build software, we need to keep that in mind. To facilitate building software, we want to abstract. We want to use microservice concepts. We want to have APIs. We want to use open source and use many different frameworks to quickly build applications and experiment fast. And we want to build that for many different devices, no matter if it's my mobile phone or my laptop or your tablets. We need to build software that is workable in many different devices. And at the same time, all of these devices need to talk to each other. So we have applications that are completely distributed at times. So how do we do that? And all of this is happening at a very fast pace of innovation. New frameworks, new open source projects, new services, new cloud providers, every single day. But pace, being fast, is important. Otherwise, you're out of business. If you innovate, you can keep your business afloat. How do you innovate? Well, innovation generally happens by experimentation. We try things out. The more we experiment, the more feedback we can get from our customers, our users, the more we can get new ideas on how to make our products better. Whatever your company is doing, make sure that you can experiment quickly and fast so that you can innovate faster. And actually, our CEO, Andy Jassy of Amazon Web Services, always says, invention or innovation requires two things: the ability to try a lot of experiments, but also not having to live with the collateral damage of failed experiments. So how do we make experimentation cost-effective? Right? We want to experiment without the burden of big costs attached to it. And that brings me to the point of, that is the reason why we want to change the way we build applications. Modern application design allows us to actually iterate faster, iterate quicker, experiment more often. What do I mean with modern applications? I mean an application that is completely modular, bits and pieces of application developed by different developers, applications that are fully automated, fully deploy out, fully roll themselves back, completely scalable, elastic, automatically adjust to the user. Resilient, they should run 24/7, anytime, all the time, without failure. And, of course, be secure. And how do we achieve that? By offloading a lot of the hard work to a cloud computing provider. So we also need to build these applications in a cloud-native manner. So if I want to do that, what do I need to change? I need to change my architecture. I need to change the way I actually operate the software, run the software, and I need to change the way I deliver and deploy that software out. So let's go to these step by step. The first part is about architecture. Traditionally, when we build applications, right, we build them in a big package, a big monolith, one big application. Every software developer commits code to it, deploys it out. That does work, but it creates a challenge. If you have lots of developers, lots of functionality, any code that you commit can break anything else in the system. So a much better approach is to say, let's create microservices. What are microservices? You break up your application into all the small little functionalities that your applications has. Right? Here's my user, here's my payment piece, here's my invoicing piece. And that becomes a microservice. Why do we do that? Now we can use our own developers for that microservice. We can build on the own data structures, the own kind of SLAs that we want to tie around it, and have them interact with each other. Developers can work on their microservice independently. So how do they communicate? Probably nothing new to you here, right? APIs. Microservices talk to each other via APIs, but we can also build architectures that are event-driven. So one microservice can call another microservice via an API, but if something changes, it sends events to other microservices to update what happened. That's how we collaborate between these new microservices. Now, from an AWS perspective, we want to make that easy for you. So different services that can help you to build this kind of microservice concepts and build the API and messaging bus. Amazon API Gateway is a great and efficient way to build your APIs in front of your microservices. Any client, no matter if it's from the outside, from a mobile phone, from a browser, can now call your initial microservice. Notifications between microservice to microservice can happen with queuing. Amazon SQS allows us to have a fully managed, simple queue, or notification using Amazon SNS. Now, sometimes it requires a little bit more than just a simple notification or an update. If you need to do a more complex kind of logic, then you can rely on things like AWS Step Functions, which allows you to orchestrate how microservices in your environment talk to each other. Now, having said that, we talk about API and the messaging, right? That's how the microservices can talk to each other. So that's great. But what about the microservice itself? We zoom into the microservice. Why do we do the concept of microservice? It allows us to choose our own SDKs, our own programming language, our own frameworks, specific to what that microservice does. Two different microservices can have two different programming languages. And that makes sense, because different programming languages have different capabilities. But more importantly, they can choose their own data store, their own database strategy. And this is really important, because not every database functions the same. There is no perfect database. So when you build a microservice, you can choose the data store that makes most sense for what that microservice performs. And this is the reason why within AWS we have so many different database options in terms of fully managed services that are all designed for different purposes. Traditionally, a relational database like a MySQL or PostgreSQL or a SQL server might be all we need. Nowadays, that doesn't work anymore. Relational databases don't scale for high volume, for example. A key value or an in-memory database would suit that purpose a lot better. If we think about a scenario like social media, where you have lots of connections between, or relations between people or entities, can you put that into a relational database? Yes, you can, but you end up creating lots of table joins and table joins and table joins. So a better database here would be a graph database, such as Amazon Neptune. Or if I work with time series, right? IoT, sensory data, maybe I put that in a time series database. Or if I need a ledger, I can use something like Amazon QLDB. The key point here is this: because we adopt microservices, we can choose the right database, the right tool for the right microservice. So when you build your application, think about which database works best and experiment with it. It's really about the constraints of volume and velocity of data and how you query it. Now you're going to tell me, okay, that sounds great, but lots of moving pieces, lots of things I need to operate. So how do I make that easier, right? So I would say, don't be a server hugger. Don't be like that bear up here and control your servers too much. Think about serverless. Now, when I say serverless, what do I mean with that? The idea of serverless is build your application on an underlying service or infrastructure that allows you to be fully managed. No infrastructure that you need to provision, no management around it. Highly available and secured by AWS. Automatically scalable. You have 1 user, you have 1,000 users, you have 1 million users, doesn't matter. Scales out, scales back. And most importantly, only pay for what you use. Pay only for the value that you get. Only if you consume storage, only if your code runs, only then you pay for it. No more overcapacity, no more idle servers running around. And so if you think about an application stack, what do you require, right? You require physical infrastructure to run on it. You require compute to run your code. You require storage and databases to store information, pictures, images, databases. You require messaging and orchestration, how microservices talk. And then on top of it, you layer your APIs and business logic. In the old world, I need to do all of this. If I build serverless, I remove that heavy lifting. These 4 lower boxes completely become the problem of AWS and not you anymore, which allows you as a developer to focus on creating value to your business. Just focus on building the APIs and your specific business logic around it. And so when we talk serverless, it's an operational model, right? Serverless is not a single service. Serverless is a concept that spans across many different services. So if you want to run your code, right, there are compute services such as AWS Lambda or AWS Fargate that allow you to run your code completely serverless. If you need storage or databases, Amazon S3 or Amazon Aurora or Amazon DynamoDB and many others can provide you fully managed serverless services all the way to the integration layer below it. So when you build an application, think about, could I use a serverless service? One that is fully managed, scales, and I only pay for what I use. Now, if you look into running your piece of code, it boils down to 2 kind of services. Excuse me. The first one is AWS Lambda. So run your code fully managed, executed by us in a cloud environment. AWS Lambda is very good if you have short-lived pieces of code. When things happen, execute a piece of code. You know, a second, 5 seconds, a minute, 5 minutes, up to 1 hour, but rather short-lived. If I say I use containers, you use something like Docker, for example, I use containers, and I want to run them fully serverless, then I choose AWS Fargate. AWS Fargate, you push your container, we do the rest for you. We orchestrate the container, we place the container, we automatically scale out the underlying infrastructure to run your containers. So this allows me to focus purely on my code. Now, if you use AWS Lambda, there's also a very cool new functionality that we released last year called Lambda Layers. And Lambda Layers is a great way to build microservices. What it allows me to do is I can take any Lambda function and attach it to Lambda Layers. Lambda Layers are pieces of code that you can share to many different Lambda functions. Very useful when you do microservices, because sometimes there are pieces of your code that is used in many different microservices. With Lambda Layers, I can now write it once and attach it to all my different microservices, allowing me to nicely separate those responsibilities. Now, if we talk about, though, deploying code out, traditionally, in a big monolith kind of structure, it meant a lot of developers work on one build, test, release, monitor pipeline. Microservices are actually not that different. You still have the same pipeline, but you do it on all of those individual microservices, allowing us to move faster on all of those individual microservices. Let me give you a number. 50 million. What do you think this number is? This number is the amount of deployments that we've done in Amazon in 2014. That means that in average, every 1.5 seconds, we deployed new code to Amazon. Deployment. How crazy is that? That allows you to move fast. But why can we deploy so often, so frequently? We use microservice concept, okay, but we automate the entire pipeline. If I write code, I can push it. It automatically moves out. If there's any problem with it, it automatically goes back in. I'm not afraid to push code as a developer because nothing breaks, because everything is automated. And when it breaks, it automatically stops. So when you build your deployment pipeline, fully automate the software delivery. Automate the rollout, but also automate the rollback. That is very important. And the rollback should happen based on what you monitor. Of course, you monitor error rates, but you can monitor business values, business KPIs, for example. With this new release, do I sell more product? Great, keep rolling out. Do I sell less product? Roll back. Automate it. And AWS provides you with many different services that can help you build that pipeline. AWS Code Pipeline to build the pipeline. Code Commit to commit your code. AWS Code Build to build and test your code. And Code Deploy to deploy it out. And then, of course, AWS X-Ray or Amazon CloudWatch to monitor your code as such. Many different ways to do it. But what I say, which is really important, make sure you have a pipeline that automatically rolls out, but also automatically rolls back. That's very important. And when we move fast, we also need to think about security. If I move fast, I cannot compromise security. Security is top priority. So when I move fast, how do I keep secure? Well, if you go into an AWS environment, there are many different services that can help you secure your environment. Around identity, who can access, who can control certain things. Around infrastructure security and encryption, build your virtual private cloud, encrypt everything. But most importantly, have detective controls. So whenever a change happens to your environment, you can identify it and immediately make sure that it is compliant with the kind of rules that you apply. AWS CloudTrail will allow you to log any activity in your AWS environment, any change, right? And not only log, I can monitor it against AWS config and AWS config rules. So any of these changes goes through a validation of rules that you set. You set the rules. It validates. If it's okay, the rollout was successful. If it's not, you can immediately take action. Revoke access, roll back, delete the user, send an email. Up to you. But it's different from the traditional model of when something goes wrong, somebody manually looks at what happened and then makes a decision. That's not good. That's not good enough. It should be automated. Every change in your environment should be validated against your security requirements. And if you do that, you feel much safer when you roll out your applications. Now, before I talk about some of the other parts of my presentation today, I also wanted to invite one of our customers on stage to talk about how they have moved to AWS and changed their applications around. So it's my absolute pleasure to invite up on stage Song-Kwon Jong, who is the principal architect of Samsung Electronics, to tell us about his story. Song-Kwon?
Thank you, Oliver. 네. 아침부터 영어 강의를 들어서 힘드시지 않으셨습니까? 네. 안녕하세요. 저는 삼성전자에서 삼성 어카운트 서버 개발을 맡고 있는 정성원입니다. 반갑습니다. 편하게 잘 강의해 주셨지만 저도 역시 편하게 조금 떨리는데요. 편하게 진행하도록 하겠습니다. 요즘 점점 더 많은 기업에서 IDC에서 수행 중인 기존 서비스를 클라우드로 이전하려고 노력하고 있습니다. 저희도 그 고객에게 더 만족스러운 서비스와 제품을 효과적으로 전달하기 위해서 클라우드를 적극 활용하고 있습니다. 오늘 저는 최근 수개월 동안 저희 삼성 어카운트 서비스를 IDC에서 AWS 클라우드로 이전하는 과정을, 그리고 그때 겪은 고민과 노하우를 여러분들께 공유하고자 합니다. 먼저 삼성 어카운트에 대해서 소개해 드리겠습니다. 삼성 어카운트는 사용자가 삼성 기기에서 로그인해 빅스비, 삼성 스마트띵, 클라우드, 삼성 페어와 같은 서비스를 다양한 삼성 서비스를 결방할 수 있게 해주는 계정 플랫폼입니다. 현재 누적 사용자 10억 명을 돌파했고 1일 호출량이 25억 건 정도 되는 대규모 플랫폼입니다. 즉 삼성 어카운트는 서비스, 애플리케이션, 모바일폰, 가정기기, TV, 그리고 수많은 IoT 띵즈의 사용자와 기기의 인증 및 권한 부여, 인가를 제공해주는 서비스입니다. 앞서 소개한 삼성의 다른 서비스처럼 삼성 어카운트 플랫폼도 전 세계 사용자를 대상으로 하는 만큼 전 세계 각 권역에서 AWS 클라우드와 여러 IDC에서 수행 중에 있습니다. 다른 계정 플랫폼들처럼 삼성 어카운트도 당사 서비스의 초기부터 구축되었습니다만 그 당시에는 최신이었는데 시간이 감에 따라 오래된 웹 기술, 모놀리스틱 아키텍처, 그리고 제한된 장비에서 운영되는 경향이 많습니다. 그래서 저희는 삼성 어카운트의 리플랫포밍 계획을 세웠습니다. 첫 번째, 보시는 것처럼 첫 번째, 클라우드 마이그레이션입니다. 먼저 IDC에서 운영 중이던 유럽 서버를 AWS 클라우드로 마이그레이션 하기로 결정했습니다. 처음에는 이 자체도 쉽지 않은 결정이었던 게 무중단 서비스를 진행해야 됐고 엄청난 룰을 받고 있는 서비스를 한 번에 옮긴다는 게 쉽지 않았습니다. 증가하는 트래픽을 원활히 처리하면서 최종 목표인 클라우드 네이티브로 가기 위해서는 저희가 IDC에서 벗어나 안정적인 퍼블릭 클라우드로 이전하는 것이 필수적이었다고 생각했습니다. 오늘 주제가 될 유럽 IDC의 이전은 올해 4월 성공적으로 완료했고 현재 오늘 이 시간 중국 서버를 이전하고 있습니다. 그 다음은 마이크로 서비스로 리팩토링 하는 단계입니다. 올리버가 설명했듯이 대부분의 클라우드에서는 현재는 마이크로 아키텍처를 채용하고 있습니다. 저희가 클라우드로 옮겨간 후 다수 레거시 서비스를 도메인 컨텍스트에 따라서 기능과 인터페이스를 유지하면서 적절히 분해할 것입니다. 그 다음 단계는 리플랫포밍의 최종 단계는 컨테이너 쿠버네티스 기반의 클라우드 네이티브 인프라스트럭처입니다. 이를 통해 더 안정적이고 더 빠르고 더 효과적인 어카운트 서비스를 저희는 제공하게 될 것입니다. 마이그레이션에 있어서 DevOps의 팀 역할을 한번 살펴보겠습니다. 여기는 마이그레이션을 하게 되면 여러 팀, 즉 개발팀, 운영팀, 데브옵스팀, 그 역할 하나하나가 매우 중요합니다. 여기에서 오늘은 데브옵스 팀의 역할을 살펴보겠는데, 데브옵스 대부분은 아키텍트와 협업하면서 필요한 서버 인프라스트럭처를 구축하고 서비스를 프로비전하는 역할을 하는 인프라스트럭처 엔지니어입니다. 트래픽을 클라우드로 유입할 수 있는 API 게이트웨이를 구축하고 점진적 이전 방식을 택해서 클라우드로 유입할 수 있는 트래픽을 중단 없이 API 게이트웨이에서 먼저 받습니다. 레거시 서버 이전 전략에서는 트래픽을 1차로 받는 파사드, 레거시 앞단에 두는 것이 굉장히 중요합니다. 여기서는 저희가 API 게이트웨이가 그 역할을 했습니다. 기존 IDC 인프라스트럭처를 분석하고 테라폼을 사용해서 IDC에 대응되는 클라우드와 최적화된 인프라스트럭처를 작성합니다. 코드로 작성합니다. 그리고 이뮤터블 인프라스트럭처를 구축하게 되는데, 이때 이뮤터블 스트럭처는 IDC에서 구현할 수 없는 아키텍처입니다. AMI 기반으로 배포하지 않는다면 각 환경마다 또는 각서마다 매뉴얼 또는 반자동화의 배포를 하게 되는데, 그때마다 발생되는 것들이 스테이징에는 업데이트를 했지만 프로덕션에 빠졌고, 인스턴스 A에는 적용했지만 인스턴스 B에는 빠져있는 컨피그레이션 드리프트 현상이 발생합니다. 이러한 현상을 막기 위해서 AMI 방식의 이뮤터블 배포가 필요합니다. 이런 것들은 클라우드에서 가능한 것이죠. 그리고 CI/CD 파이프라인을 구축하는 것은 DevOps 엔지니어에서 가장 중요한 역할 중에 하나입니다. 그 다음은 DevOps의 또 하나의 중요한 역할을 하고 있는 데이터베이스 엔지니어, 데이터베이스 관리자 DBA입니다. DBA는 대개 운영팀이나 DevOps 팀에 소속이 될 경우가 많은데, DevOps 팀에서 그 역할을 굉장히 중요합니다. 그 이유 중에 하나는 데이터베이스도 클라우드에서는 매니지 서비스 중에 하나로 동작하기 때문입니다. 그래서 마이그레이션을 필요한 데이터를 분석하고 필요한 데이터만 마이그레이션하고 줄여주는 데이터 플래닝을 하게 됩니다. 굉장히 중요한 작업 중에 하나고요. 그리고 데이터를 IDC에서 클라우드로 옮길 때 보통 전용선을 먼저 놓게 되는데요. 그 전용선의 품질에 따라서, 네트워크 품질에 따라서 보통 품질과 데이터의 사이즈에 따라서 일일 또는 수일이 걸리는 경우가 있습니다. 저희의 경우는 한 수일 정도 소요가 됐고, 그 수일 동안에 델타를 저희가 체인지 데이터 캡처 싱크를 사용해서 싱크를 했습니다. 이 모든 서비스는 아마존 서비스 중에 하나인 DMS를 통해서 가능했습니다. 그리고 변환돼야 될 스키마, 변환돼야 될 쿼리들을 분석하고 그 모든 쿼리들을 수행했습니다. 나중에 말씀드리겠지만 2,500개의 쿼리를 무리 없이 다 변환하는 게 쉬운 일은 절대 아닙니다. 나머지는 데이터베이스를 이전하게 되고 클라우드를 이전하게 되면 동종의 데이터베이스를 쓰지 않을 경우가 많습니다. 기존의 레가시 DB, 저희는 오라클이었는데 포스트그레스 오로라 포스트그레스로 옮겨갔습니다. 그렇게 되면 쿼리의 대부분은 다 변환돼야 되고 애플리케이션도 그에 따라 수정돼야 됩니다. 이러한 것들을 무리 없이 진행할 수 있도록 데이터베이스 엔지니어의 역할은 매우 큽니다. 이전에 있어 가장 중요한 컴포넌트는 말씀드린 것처럼 데이터베이스입니다. 시간이 지남에 따라 IDC의 데이터베이스 장비가 노후화되는데 서비스 규모와 트래픽이 늘어나면서 더 빠른 소프트웨어와 하드웨어가 필요합니다. 트래픽은 지속적으로 증가하고 증가된 서비스 규모를 제대로 수용하지 못하면 수용하려면 마이크로서비스 기반의 클라우드 네이티브 아키텍처가 필요해지게 됩니다. 이러한 요구를 기존의 상용 데이터베이스로 해결하기에는 한계가 있었습니다. 레거시 데이터베이스는 유연하지 못하고 라이센스 비용도 무시할 수 없었습니다. 무중단 서비스를 위한 기술의 제약도 컸습니다. 모든 이전에는 늘 그렇듯이 다양한 제약이 있습니다. 보시는 바와 같이 지속적인 트래픽 증가, 유연한 DB의 확장성, 라이센스 비용, 서비스의 중단 없이 모든 것을 심리스하게 이전해야 하는 제약들이 있습니다. 레거시 DB를 클라우드로 전하는 과정에서 우리가 겪은 두 가지 챌린지를 소개하고자 합니다. 첫째, 먼저 저희는 데이터베이스를 SQL 쿼리의 85%가 호환되는 PostgreSQL로 이전하기로 결정했습니다. 레거시와 가장 호환이 높은 오픈소스 데이터베이스를 정하는 것은 중요한 일입니다. 한국에서는 포스트그레스는 그 영역을 좀 더 넓혀가고 있는데요. MySQL에 비하면 레퍼런스가 좀 적은 것은, 그리고 저의 경험이 많지 않았던 것은 처음에 좀 제약이었습니다. 이러한 챌린지를 저희는 AWS 전문가를 통해 글로벌 고객의 데이터베이스 전환 사례를 공부했습니다. 그리고 포스트그레 데이터베이스의 운영과 모니터링, 쿼리 변환 교육을 별도로 받았습니다. 네. 여기서 혹시 지금 포스트그레 SQL을 사용하시는 분들이 계신가요, 여기서? 한번 손 한번 들어보시겠어요? 예. 올리버. 예. 예. 저기 몇 분 계시네요. 예. 그래서 오픈소스 데이터베이스에서 영역을 확실하게 넓혀가고 있고 레퍼런스도 점점 많아지는 경향이 있습니다. 둘째, 삼성 어카운트는 저 앞서 소개한 것처럼 삼성 서비스의 인증과 권한을 담당하는 서비스였습니다. 그래서 한번 장애가 있게 되면 그 여파가 타 서비스에 크게 작용합니다. 이러한 장애를 막고 안정적으로 이전하기 위해서는 무중단 서비스를 위한 방법이 필요했는데 저희는 말씀드린 것처럼 한 번에 데이터를 옮기는 것이라 점진적으로 데이터를 옮기는 과정에서 과정을 진행했고 이러한 과정은 보통 10여일 정도가 소요됐습니다. 그럼 데이터베이스 이전 과정에서 저희가 실제 진행한 것들을 좀 더 자세히 살펴보겠습니다. 보시는 것처럼 22주, 또 단번에 진행된 건 수개월이 걸렸고요. 먼저 저희는 유럽 지역에 있었던 기존 오라클 데이터베이스를 22주 만에 완벽하게 오로라 포스트그레스로 교체할 수 있었습니다. 이 데이터베이스에서는 수테라바이트의 사용자 기기 데이터 3만 이상의 QPS 2,500개 이상의 쿼리를 실행 중이었습니다. AWS 마이그레이션 전문가 협업해서 기존 테이블 스키마 및 쿼리를 AWS 스키마 컨버전 툴 SCT를 사용해서 변환하고 일부는 매뉴얼 변환했습니다. 모든 게 자동으로 변환되지는 않습니다. 일부 10% 정도는 매뉴얼 수정해야 되는데 이 부분이 좀 어려운 부분입니다. 그리고 전문가들과 좀 더 협업해서 데이터를 이전하는 데 쓰이는 서비스, 데이터 마이그레이션 서비스, DMS 서비스를 사용해 이니셜 로드하고 그 나머지 싱크를 진행했습니다. 이 슬라이드가 바로 기존의 IDC 레거시 데이터베이스를 클라우드로 이전하는 과정의 모범사를 보여주는 전체적인 아키텍처라고 생각합니다. 보시는 바와 같이 IDC 소스 데이터베이스에서 데이터 파일을 익스포트해서 1번입니다. 익스포트해서 데이터 덤프를 받은 것으로 아마존 RDS 기존의 소스 DB와 같은 동종의 DB에 임포트 시킵니다. 그리고 DMS 서비스를 통해서 오로라 포스트그레스 SQL로 변환해서 로딩합니다. 그리고 그 사이에 벌어진 델타분은 위에 보시는 CDC Change Data Capture 서비스를 사용해서 싱크를 하게 됩니다. 이러한 과정을 마치고 나면 모든 데이터가 복제되고 싱크되어 있게 됩니다. 네. 삼성 어카운트를 저희가 클라우드 기반 데이터베이스로 이전한 결과 데이터베이스의 라이센스 비용 그리고 CDC 솔루션 비용을 크게 낮출 수 있었습니다. 무엇보다도 오로라와 같은 관리형 서비스를 이용함으로써 오픈소스 DB를 통해서도 상용 DB의 성능을 얻을 수 있었다는 점에서 저희에서는 중요한 경험이라고 저희는 생각합니다. 이러한 경험과 노하우를 토대로 내부 애플리케이션 개발자들이 트래픽이 늘어남에도 좀 더 유연한 데이터베이스로 활용할 수 있게 되었습니다. 앞으로 삼성 어카운트는 타 계정과 연동해서 어카운트 링킹을 확대하고 사용자 편의를 높일 수 있는 기능과 인프라스트럭처를 더 쉽게 제공해서 성장하도록 하겠습니다. 그리고 오픈 아이디 커넥트, OAuth2와 같은 표준 프로토콜 사용해 더 많은 기능을 제공하도록 하겠습니다. 그리고 성장하겠습니다. 감사합니다.
Thank you so much for this presentation. What a great story to hear, how some of these large companies like Samsung Electronics are making great use of these newer kind of designs and services. And so I wanted to take a next step to talk about portability. If you build applications, I said earlier we need to make sure that they work on any kind of device that my end user or end customer wants to use. Now, we talked about the bottom part, right? We talked about serverless and containers. It allows us to port code easily from the underlying infrastructure, the underlying cloud provider. No problem, easy to port. And because we use APIs and microservices, any client that can talk HTTPS can talk to my microservice, meaning any client can easily talk to it, which means my entire backend easily portable. How about the client side? iPhones, Androids, lots of different devices out there, tablets, computers. Do I need to develop applications natively for all of them? I can, but that's a lot of work. So that's why there are frameworks out there like React Native or React in general, or Ionic, that help me to kind of build applications once and have it available on many devices. But what is really driving this much more, such as, for example, progressive web apps, which look like a native application in your phone, but are actually a web application, are the web standards. HTML5 allows us to run very complex applications in your browser, easily. Now, when I say complex, I figured I want to give you a demonstration today with all of your phones that you can run a very complex application. But before I get to that application, let me just explain what I'm trying to demonstrate to you. If you haven't heard of something called photogrammetry, photogrammetry is the ability to take pictures of a place or an object in multiple angles, and if you do that often enough, you can calculate a 3D object representation out of that object. And so I'm going to try to do now is, I'm going to do a photogrammetry on my face, and then we're going to try to send it to your phone using HTML5 and Amazon Sumerian, our service for 3D applications. So let me switch over here to something I pre-prepared. So when I was at home, I went ahead and I took a lot of pictures of myself, like this, click, 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 around my face, on my head, pictures like this. And if you do that, what you can render, and I rendered this in an AWS environment, then brought it to my laptop, I can actually render a 3D point cloud out of that. Now, if I enable the pictures here for a second, you can see that it allows me to create a nice calculation of the distance points of my face. And that's cool. If I can do that, I can also render a wireframe of my own face. So here you see, for example, with just about 80 pictures that I took, I created a nice wireframe out here. And if I then apply the texture, off we go, and we get a 3D representation of myself, just out of a few pictures. Now this I rendered in my AWS environment, but I said I'm going to send it to your phone. So how do we do that? HTML5. HTML5 has WebGL standards allowing to render 3D objects in your phone. So I loaded it up into something called Amazon Sumerian, which allows me to give you a link to load up that 3D object. So if you want to try this out, you can go to this URL that I just flash on the side, bit.ly/ollie-3D, and I'm going to do the same here on my laptop. And here we go. It will load up an Amazon Sumerian experience. So the ability to load up complex applications into my browser, into your phone, and off I go. In my web browser now, I have a picture of myself in a 3D format. How cool is that? It's a little bit creepy. See, you got me 3 times. Ah, big Ollie. And it should work in most of your phones too. Awesome. Now, the reason I show you this is because 3D applications was once something very complex, right? You need to write an application that you can download and run it on a powerful computer. Now it runs on all your phones, no problem. Portable web standards allow me to create complex applications everywhere. Which brings me to everywhere. How do we build applications and code that can run everywhere, at the edge, or on a robot? So let's talk about that for a second. It specifically goes into the space of IoT. Lots of devices out there that we want to render intelligent. With AWS, we kind of want to make that easier for you. So if you run IoT devices, you build IoT devices, we provide you with the services such as Amazon Free RTOS that provide you with the device software that you can deploy, or AWS IoT Device Tester to test your devices, build your devices. And then there are services, control services, that allow you to manage how they talk to each other. AWS IoT Device Defender to make sure if a device is compromised, somebody hacked into it, that you're aware of it, that you can fix it, all the way to data services, right, where you have events that you can set up and you can run analytics on these devices. And we do all of that to really drive outcomes and intelligence, get insights from my devices and have them talk to each other. And so, if we talk IoT, one of the obvious applications of IoT is robotics. And robotics is really undergoing a fundamental change right now. We see robots everywhere, no matter if it's in logistics or constructions or agriculture. I was just down in Australia last week, and we worked on a robot that actually has a hand and can pick apples automatically from the trees. How cool is that? And then I take the airplane and I come to Seoul and I go to my baggage belt to take my luggage and I don't know where it is and there's a robot coming to me. Hello, how can I help you? Where's your luggage? Robots everywhere, right? As a matter of fact, we invest a lot of work into robotics within Amazon. Only recently, we announced our new Amazon drone, which is the drone that we use for Prime Air. And there was a lot of engineering that went into this, a lot of testing and experimenting to get that drone running. But you might say, okay, it's a drone, so what? This drone is a little bit different. Let me show you a video of it. What we changed on this drone is this: when it takes off, it's just like a normal drone, right? Drone comes up, but when it reaches a certain height, it goes into flight mode, and it will flip itself into a horizontal mode, into a vertical mode. And now we can use the aerodynamics of the air to let the drone hover. And that allows us to reduce the amount of electricity consumed. It allows us to fly faster, safer, and longer distances. And when we're done, and we need to land, the drone goes back up, goes into the other mode, and then slowly lowers itself onto the platform. What you saw here, even though experimental, is actual footage of that drone flying completely autonomously. Nobody controls this drone. This drone was flying by itself. And that is a good application of robotics. We will use this to, for example, deliver packages. Now, I said we invest a lot of time into robotics. And as part of that, we also invest into what is called the Robot Operating System, ROS, which is an open source operating system for robots, so to speak, out there. We continue to invest in that, and we also want to make sure that anyone out there can easily build their own robot applications. That's why we launched something called AWS Robomaker that allows you to easily develop, test, simulate, and deploy intelligent robots at scale. So it comes with a simulation environment, right? Where you can simulate your robot, have it navigate around, try, learn, and then, of course, develop against it, and eventually deploy it out and manage your robots out there. Now, robot operating system is really cool because it comes with a lot of components. It comes with the abilities to visualize and navigate, etc. So I figured it would be nice to maybe try this out in a live demonstration. And so with me here, I brought a little robot. Let me just bring this up first. Plug it into the battery. There we go. All right, let's have a camera on this for a second. So with me here, I brought a Turtlebot. Turtlebot is a great robot to experiment with if you never used a robot. You self-assemble it. It comes with a Raspberry Pi. It comes with an OpenCR board. That board controls the wheels here, so the robot can drive around. Because it is a Raspberry Pi, I also attached a webcam to it. This is just a normal webcam. But most importantly, on top here, if you wonder what this is a laser distance sensor. So a sensor that keeps spinning, and there's a laser that goes around, and it allows me to identify the distance that I have to it. So let's try this out. I want to try to navigate this robot and show you the visualization tools to find the distance, identify walls. And so with me here, I brought a maze. So I'm going to put that robot here into the maze first. And then I'm also going to load up my visualization software here. All right. And now what you can see is, I'll just load everything up here. What you can see is the robot operating system comes with a visualization tool that allows me to visualize what the robot is currently doing. And now if you look closely, you see these green dots here. They are actually distance sensors. So if I start driving the robot around now, so I'll give this robot a little push. There we go. You can see that the laser distance sensor is updating its values. So if I drive the robot forward, you can see that the laser distance sensor and the visualization tool is now mapping out the entire environment. Don't run into the wall. Drive the boy forward. Just around the corner here. Got lots of interference. Bring him back. And it's currently connected via Wi-Fi, so some of the instructions I'm sending him is a little bit delayed, so I navigate carefully. And the really cool thing now, what you happen to see on my screen here, is that the laser distance sensor allows us to do what is called SLAM, S-L-A-M, simultaneous localization and mapping. So as the robot drives around, it finds out the area that it navigates in. So it didn't know this maze, but now it could map it out like this. So as you see now, it has learned where the walls, where the robot can drive around. And when I learn like that, the obvious next thing that I could do, by the way, I also have the camera coming through here. What I can now do is I can say, load my navigational program and try to see if the robot can now self-navigate, because the robot has learned its environment. So you can see now that the robot has learned this environment, and it roughly knows its location. And you see lots and lots of these small little green arrows around it. And these green arrows indicate where the robot thinks it currently is in the previously learned environment. Now, if you look at all of these kind of small errors, you can see that they're not quite aligned, right? Because the maze looks very similar. So what you can do is you can give the robot a push and say, try to navigate yourself a little bit forward. And if I do that, you can see the robot is now navigating itself, and these arrows start to concentrate. And you can see the maze now aligned with the laser distance sensor that hits. So I give him another navigational goal here. I say drive over here. Drive over here. You can see that the robot now slowly learns how to self-drive itself into that kind of place. I can see it's very careful because the laser distance sensor is finding its way. But this allows us to now fully, completely navigate that robot around by itself using operational goals. I think I just killed my program. He's like, wow, where do you want me to drive? But what I wanted to show you here, which is really cool, is, I think my visualizer crashed. Yes, one couldn't. There we go, he's back. He was thinking. The robot had to think. Okay, there you go. All right, he's happy. He found his way. Now, the really interesting thing about this, though, is really, let me just stop him there. There you go. The really nice thing about this, though, is what you can do with these visualization tools, what you can do with the robot operating system. So not too long ago, building a navigational capability for a robot like this would be very complex. But now I just have this framework, the robot operating system, making it really easy for me to do that as such. And now the other thing, what you have with AWS also is everything that you build, the actual physical robot here, can be controlled by my environment, but I can also simulate millions of environments in my cloud computing environment, learn from it, and then bring it back to the physical world. So let's talk a little bit about overall distributed applications. When we talked IoT, we talked robotics. How about applications? There are a few things that have changed. Right? The first one is we have lots and lots of devices. Phones, tablets, computers, robots, IoT devices. And all of them kind of share a certain ecosystem, right? They don't just serve a single purpose, they start connecting to each other. We have customers and users all across the world that all desire to interact with each other. But the laws of physics, they haven't changed. Physical distance incurs latency. From here to the US, you always have a certain latency. From here to Europe, you always have a certain latency. You can't change the laws of physics. So what if I need to build an application that requires low latency? I need to adopt different strategies. I need to think about how can I use data stores that are globally distributed? How can I deploy some of my logic closer to the edge, closer to the device maybe that I have? How do I handle network connections that drop gracefully? Right? And how do I do caching properly? And so if I go through that, and I start off with, let's say, data stores. With AWS, we make it really easy for you to globally distribute your data stores. You have a relational database. With Amazon Aurora, you have something called cross-region replication. Click of a button, you now have your relational database in Seoul, in US, in Europe, wherever you want it. And it even with multi-master write, so you can write into all of these locations. You want non-relational, NoSQL, Amazon DynamoDB, cross-regional replication. You have objects, Amazon S3, cross-region replication. How do you decide which region you go to? An end user uses your app, you resolve the connection with Amazon Route 53 and use latency-based routing. It will automatically send the connection to the right region. Your user is in Seoul, you direct him to Seoul region. User is in Singapore, you direct him to Singapore region. And you can even bring some of the logic to the edge locations from our CDN, from all of our points of presences across the world, using something like AWS Lambda at edge. And with Amazon CloudFront, I can make sure that I cache all the assets all over the world at the edge locations that we provide. All of this fully managed, right? Makes it really easy to globally distribute it. I also said handle network connections, intermittent network connections, good. Think about a phone, right? You have mobile data, 3G, 4G, 5G soon, right? But sometimes you lose connections. Now, I think you all had this experience before. I had this experience before. You have an app, you lose connection, and the app doesn't work anymore, or it crashes. It's a horrible experience. But a lot of apps are designed to always have connectivity. But that's not the case. So you want to build a user experience and an interface that is responsive and collaborative, even when you don't have internet connection. And so we want to make that easier for you. That's what AWS AppSync is designed. It allows you to build those user interfaces that are responsive, have data stored on the device, and synchronize with the cloud environment and other users when connection comes back. Right, making it a smooth experience, even when the connection drops. And the same goes for your IoT devices. With IoT devices, sometimes they're very far away from a stable internet connection. 2 weeks ago, I was in New Zealand, and we worked with a farm, and they had like lots of sheep there. And all the sheep had devices attached to monitor where they walk around. The challenge here was getting internet connection to some of these remote locations is really expensive because you got to do satellite. So what they did instead was they deployed some of that logic onto the farm, and the farm would only connect to the internet once in a while to synchronize that information. That's a great idea. Now, we want to make that easy for our customers. If you use AWS Greengrass, you can have your logic that you build in the cloud, then deploy it out to the edge. Your logic runs, it collects information, and it can disconnect, and it can continue to operate. And when it reconnects, it synchronizes with my cloud environment only the information that I require. So think about the situation when connectivity is difficult. There are services that can help you achieve this still without too much effort. Now, why do we have IoT? Why do we have all these devices, right? Because we want to collect data. Why? The more data we collect, the better we can make decisions. Data is an asset for any company out there. A company that uses their data well will perform so much better than companies that do not make use of their data. And I want you to think about data as an asset, not a cost, an asset to your company. So stop throwing away data. Don't delete data. Keep it. Make it available to as many users as you possibly can within your business, and give them the tools so that they can make intelligent use of that data, find patterns, analyze, build machine learning models around it, learn from it. I say, don't stop throwing it away. Why do I say that? Because it has become so cheap to store data. To give you an example, if you take something like Amazon Glacier Deep Archive, this is the lowest cost storage available in the cloud right now. It's even much lower cost than on-premise tape. As low as 0.00099 gigabyte per month. That's an incredibly cheap rate to store with a very high data durability, your data. So when you build data lakes, you don't need to worry about cost anymore. But I need to design it correctly. So I, as a developer, I want to make sure that I can quickly and effectively get insights from my data, help my business. To do that cost effectively, I need to decouple compute and storage. Traditionally, I have a data warehouse. The data warehouse stores the data warehouse is where I send my SQL query. I want to store more data, I need to get a bigger data warehouse. Data warehouses are expensive. So you are careful which data you're storing. So that's not good, because there's lots of data out there. So what I want to do is, I want to store my data in just a storage service. And only when I run a report, only when I build a machine learning model, then I pay for the computational power. And the other thing is, sometimes we worry about the structure of the data. What's the schema? How do we store it? Don't worry about it anymore. Data transformation has become very cost effective. But to achieve that, you need to build a cloud data lake. A cloud data lake that allows me to use a storage service such as Amazon S3 to store all my data in different formats, different varieties, structured, unstructured. And then around it, I built analytic services, right? Serverless data processing. Services such as Amazon Athena allow me to run SQL queries completely serverless of an Amazon S3 bucket. How cool is that? Well, I built real-time analytics around it. We have a broad platform with many different services that allow you to build an effective data analytics pipeline. Build your data lake on Amazon S3, use something like Amazon Lake Formation to quickly set up a data lake. And then use the different analytics tools that make sense for you. Amazon Athena, run an SQL query on top of it. Amazon EMR to maybe run your Spark or Hadoop jobs against that data lake without loading the data. And lots of services that help move your data in and out of your environment, from on-premise to your locations, to your cloud, transform it, or even analyze it in real time. And lastly, lots of services that can help you with machine learning and AI. So let's talk about that. AI and machine learning. Let's talk about that for a second. This is a very interesting space right now. Machine learning is nothing new. It's been around for a long time. But what has changed is the capabilities that we could do at a fraction of the cost. And part of that is because of cloud computing. Now, I want to talk about the technology. But before I talk about the technology, I want to give you a few examples from Amazon and how we make use of AI and machine learning. I showed you a video of a drone, right? That was one example of robots. We use a lot of robots in our fulfillment centers. When you place an order on Amazon.com, most of the time in the US, it will hit a fulfillment center that has Amazon Robotics implemented. What you see here at the bottom is a robot that basically drives around the shelf that sits on top. And the idea is, instead of somebody walking to the shelf, getting the products they need, we bring the shelf to the packer. So the shelves will drive there, and all the packer needs to do is take out the goods. Next shelf comes, take out the goods. That's it. We simplify that process. We do that for two reasons. The first one, the picking becomes more effective, faster. But the second one is, we can compress our fulfillment center. We can reduce the amount of size of space that we require, because all these shelves can stand right next to each other, compressing the size of floor space. And that allows us to save money on storing goods cost savings that we can give back to customers, reducing the cost of products. Now that sounds great. Now let's try to build this. I'm a software engineer, right? So if I want to build this, what do? I create a database. The database has tables, shelf number 1, shelf number 2, right? Then there are bins, bin 1, bin 2, bin 3, and another table, product 1, 2, 3, 4, 5, and I just join them together, all right? That should be it. If the robot drives into the packing station, I change my database, -1. If I put something back in, +1. Robot drives off, no problem, done. The reality is not like that. In reality, what happens is sometimes people take the wrong product off the shelf. Sometimes things fall out. Sometimes the wrong product is being put into the wrong bin. And now your database is inconsistent with what you have in the fulfillment center. Complete chaos. So how do I fix that? All right, let's implement a little trick. Every time that robot drives into the packing station, it goes through the arrival tower, it drives through, we install a camera, we take a picture. The robot drives through, the picking happens, no. Robot drives back out, we install a camera, take a picture. What do we do with these pictures? Machine learning. We implement computer vision on top of those two pictures. And that computer vision model identifies the bins and then identifies which bin has items removed. If it is the correct bin, the robot will just continue. If it is the wrong bin, the robot will drive to the side and somebody can manually see what went wrong. And it comes with one additional capability. If you look on the right side, we run an activation and binary map over those bins. And with that information, we can identify how much space is left in that bin. And now we can calculate what is the best product to store in this bin, so we optimize the space as best as we can. This computer vision model was implemented a bunch of years ago on a cafe framework. Within 2 days, they had a working model. That's how easy computer vision has become. Let me give you another example of computer vision. Amazon Fresh is our online grocery delivery business. So you can shop online for your groceries. And what is the biggest challenge with groceries? Perishable goods, such as fruits or vegetables. Why? Right? I can't smell it, I can't feel it. Are they good? You click online, that's it. But we don't want to ship you bad fruit. So how do we do that? Well, we actually build a computer vision model that identifies if a vegetable or fruit is ripe or if it has gone bad. And the way we do that is, as these vegetables or fruits arrive, they're placed in a small basket. And that basket or that tray here actually drives on a belt, and there's a camera that takes pictures of it. Now, with those pictures, we built lots and lots of machine learning models that learn over time, how does a good strawberry look like? How does a good potato look like? How does a good apple look like? And how does a bad strawberry here look like? And then we instruct them to be removed. And now you're going to say, okay, but could I not just have one person that just does that all day long? Right? Why build a computer vision model? Somebody still needs to take it out to reduce failure rates. As a human being, if we do the same thing over and over and over again, we get fatigued, right? We make mistakes. This helps us to increase the success rate of finding the bad product using computer vision. And now you can bring that to the next level. You can say, what if I want to build a customer experience where I can go into a convenience store, I can pick up from the shelves anything I want, put it in my pocket, put it in my bag, and just walk out. And I will have automatically my credit card charged for what I bought. Great experience. No cashier, no queue, no waiting. That was the idea that we had 8 years ago when we started building Amazon Go. Amazon Go allows you to just walk in, take off anything from the shelves, walk out, and we charge you for it. How do we do it? We use computer vision models with lots and lots of cameras that are installed in the ceiling, in the shelves, and we merge it with sensor technology, sensors on the shelves everywhere. But how does that actually look like? If you walk into a store like this, look up into the ceiling, and you'll see hundreds of cameras hanging around. All of these cameras in different angles. And what these cameras help us to do is, we can, as you walk into the store, identify you, okay, this is customer 123. As you walk around, we detect what you're doing. And as you walk out, we know what you bought. Now, you might say, okay, how does that look? This is how it would look for our computer system. This is actual footage that you see from our Go store. So the top video is our Amazon Go store in Seattle, the first one that we launched. This is during lunch hour. Very busy. You see so many people swarm around. But we have the ability to identify all those individuals as they navigate around in this store. At the bottom, you see the more detailed computer vision model that identifies your movements as you're doing. And what you see here specifically here is two people grabbing the same product at the same time. Who are we going to charge? These are interesting edge use cases that we're building into this. And so you train that on lots and lots of video material that you have. But that's sometimes not good enough. You want even more material. So what you see on the left side here is actually not camera footage. It's a 3D world. It's a 3D simulation of the Amazon Go store. And with that simulation, we can continue to try things out and have the computer vision model learn from it. Now, our idea with AWS now is, we learned a lot of things in Amazon on machine learning. Can we make that available to anyone out there to use it? And we want to put machine learning into the hands of any IT professional out there. And we kind of see it as a three-layer approach. The top layer, fully managed AI services, computer vision services, facial recognition services, document extraction services, language services around voice and transcription and translation, or chatbot functionalities, all the way to things like Amazon Personalize. Build your own recommendation engine with the same algorithms, the same machine learning models that Amazon.com, but with your data. Amazon Forecast, build your forecasting. The top layer does not require you to build any models or understand any machine learning or data science. It's an API, you integrate it into your application. That's great. The middle layer is to say, what if you want to build your own kind of model with your own data? How can we make that easier? I'm going to explain a little bit more on that in a bit. And at the bottom, we look at all the different frameworks that we want to make available for you and reduce the cost of doing machine learning. If we take that top layer for a moment, these are building blocks that we can use to build an actual application. Thank you. So let's say, for example, I have a call center and I want to get better insights into what are my client representatives talking on my call center. So what I could do is to say, let me use something like Amazon Transcribe every conversation that is being had, then use something like Amazon Comprehend to analyze the transcribed text. What are the people that are being talked about? What are the problems, the key entities being talked about? And now I can plot that out and get information. Use it with my business intelligence tool and say, here are the common recurring problems that customer ask me for. Maybe I can fix that. Maybe that's a different way to approach it. The top part are building blocks that you can easily use to build an application. Let's focus on the middle part for a second. This one's really interesting. It specifically revolves around a service we call Amazon SageMaker. Amazon SageMaker allows me to build, train, and deploy machine learning models. These are 3 different operations that you can use independently. So you can say, I build and train in AWS, but maybe I deploy onto my phone, onto my data center, doesn't matter. Or you can say, I can build on my laptop, but I train in the cloud. So these 3 operations can all be used together or can be used separately. But the build part here is where I want to spend some time on. This is really useful. We provide you with built-in high-performance machine learning algorithms for common problems, meaning you get access to algorithms that Amazon has built. And recently, we also launched a marketplace for it, where some of our partners are building machine learning models and algorithms. And you can use those algorithms to build your own model. All you need to do is you bring your data in, and you train it on the algorithm without the need to write the algorithm itself. So that makes it accessible to a lot of developers, right? We might not have the data science knowledge, but we know how to integrate things. So let's say for a moment you want to build an object detection model. There's an image classifier and an object detection algorithm built in with Amazon SageMaker. So all you do is you bring pictures. You say, here's, I don't know, let's say the water bottle here that I want to detect. Water bottle, water bottle, water bottle. You just bring the pictures in. The machine learning model will automatically learn from it. You didn't have to know how do neural networks work. You didn't have to know how to build computer vision models. You didn't have to know how to build a machine learning algorithm. You just bring the pictures and the model learns from it. That makes it really easy. Now, computer vision has become very accessible. And I showed you a lot of videos, right? And you look at those videos and you say, yeah, that must nice, but must require lots of expensive equipment and hardware. No, not really. I'm going to try to do a live computer vision demo right now here on my laptop. Those models have been trained in AWS, and I then push them right here onto my laptop. Now let me first set it up, and then I switch over to the correct screen. So with me here, I just brought a very normal camera. This camera is just connected via HDMI to my laptop. And now I'm going to load up a computer vision model that has been trained on some of the common objects and takes the video feed here right from my camera. So you can see in real time, this is not rocket science anymore. I can easily identify myself as a person, can easily see the boundaries here and identify the different objects. Let's try out, see if I put in a bottle. You can see that it identifies that bottle easily without any problem. TV monitor behind me. And this just runs off my laptop right now here. Can run off your phone, as a matter of fact. If you're interested what we're using here, this is a model called YOLO, Y-O-L-O, YOLO, you only look once, that we used here, that we trained. And just to show you that this is live, you can all have a wave into the camera for a second. Lots of people here. So that's how it looks like for me here. Cup monitor, TV monitor right here. Now that's cool, right? So object detection is pretty easy to use nowadays. So if I can do that, I can take it one step further. And I can say, what if I not only try to identify the object, but I even try to identify the person? And so there's a very cool open source framework out there called OpenPose. And try to have a look at it, because it's pre-trained already. And what it allows me to do now here, it allows me, let's make this big, loading up the model. It allows me to actually identify my movements. So if I just point this out here for a second, just try this out, see how robust the machine learning model is on this one. You can see that it identifies my movements. I can stand around like this, and turn around, what was that? And I can then also run a heat map. So if let's say I run a heat map over it, I can easily identify, again, myself, the heat map on how I'm navigating around, no matter how fast I'm moving. This is just computer vision. No special equipment can run on any web camera right now here, and we can identify individuals around like this, with lots of individuals sitting here, for example, just using computer vision. How cool is that? So computer vision has really become something that is so easy to use nowadays. But you're going to say, okay, thank you, that's cool, but why do I do that? Well, you saw the Amazon Go example, right? That is using a lot of these people detection algorithms. But if you have CCTV cameras hanging around, we have customers that are using it in a shopping mall to understand, where do people navigate? How do they navigate around in a shopping mall? We have it in public transportation scenarios where people try to understand, where too many people, where not enough people. Is there a problem? Is there a safety risk? Is somebody fighting someone? You can identify that now really, really easily. Now, let's talk about the last layer, though. So the last layer is really about how can we make sure that you can use the tools and frameworks that you want to use, without any limitation, while making sure that machine learning is cost-effective for you. And so it starts off by obviously making sure that you can use any framework of your choice on the AWS platform. You want to use TensorFlow, you want to use MXNet, you want to use PyTorch, you want to use Caffe, Onyx. It's all there. Not just the ones listed. You can pretty much use any framework you want. The ones listed are the ones that we continuously optimize the platform for, so that you get a performance boost when you use TensorFlow on AWS, for example. But that's giving you choice. The other thing is, how can we make it cost-effective for you? So if we talk cost for a moment, a lot of people think machine learning is primarily expensive because of training. Training machine learning models must be very expensive. Lots of data, trained, complex. The reality is, training is not the most expensive part. Most of our customers, the majority of the cost, comes from the inference, making the prediction. Why is that? Think about that computer vision model that I just shown you. That computer vision model requires GPU capabilities to actually run. Now, when you make a prediction, you might have 1 user, 2 users, 3 users. They don't use the full capacity of the GPU. But if you consume a GPU, you pay the full price for it. So you pay a lot more for what you require. Remember when I talked about serverless? How important it is that you only pay for what you use when you use it? We want to give you the same capabilities now for machine learning. That's why we released 2 different things. The first one is Amazon Elastic Inference. Amazon Elastic Inference allows you to attach and detach small increments of GPU capabilities for your neural networks when you make a prediction. That allows us to be scalable and elastic. Add small increments to it. When there's more traffic, remove it when there's none. And when you remove it, you get cost savings. As a matter of fact, When we launched this, our customers found that they save up to 75% of cost when they go granular like this. And the other thing is, we also worked on a custom fabric called AWS Inferentia to reduce the cost of inference by up to 10%. Inferentia is going to come a little bit later this year online on the platform. So last thing before I leave you for the rest of the day, what if we want to build machine learning models, but we actually don't have training data? Right? Because for machine learning models, we actually need to train data. Well, the first one is I go to AWS and see if they have a fully managed service for me. But what if there's none that serves my use case? That is the space where maybe reinforcement learning could come in handy. Learn as things are happening. What's reinforcement learning? Reinforcement learning allows me to learn by interacting with the actual world. So you say I create a scoring function, a reward function. This is good, this is bad. And then the model will slowly learn from it. Bear with me, it's only three minutes left. I think I need some soju. So, the way it works, scoring function good and bad. So if you take the example of, let's say, vehicle routing, right, and you say, I want to find the best route, create an algorithm that finds the best route, you could use reinforcement learning for it. So you would define a state, current location of the driver, distance from home, etc. And you would define actions, pick up, deliver, etc. And then, the most important part, you define the reward function. Positive when we deliver on time, negative when we don't deliver on time. Now, these reward functions can be more complex. But if we do this is sufficient if we run a lot of simulations to create a reinforcement learning algorithm or model that will find the best possible route. Without any training data. We just simulate it over and over and over again. And so it's very useful in the space that can be easily simulated, like robotics, industrial controls, autonomous vehicles, etc. And we want to make reinforcement learning easy for you to use. So we released something called Amazon SageMaker RL, which is our fully managed service for reinforcement learning that provides you with algorithms, but also provides you with the simulation environments, such as OpenGym or Amazon Sumerian. You know, earlier I showed you that 3D picture of myself. I sent it out via Amazon Sumerian. Well, turns out you can also use Amazon Sumerian as a simulation environment. So let's try this out and actually try to create a simulation environment and run a reinforcement learning model on top of it. So let me just load up my Amazon Sumerian scene first. This will take a little bit of time. But what I did is I created a virtual world in Amazon Sumerian, and I attached it to Amazon SageMaker. And Amazon SageMaker runs a reinforcement learning model on top of it. Now, I defined a few things. Just make this a little bit bigger. So I defined this world of this wonderful unicorn trying to chase the hot dog. Right, so those are my actors. That's a good example. Right? Now the unicorn now has actions. The unicorn can spin, and it can move forward, and it can spin. Right? And if I reach the hot dog, then that would be a reward. Right? Come on, get the hot dog. Yay, that's a reward. All right? And now the trick is, now I have my simulation environment. Everything is defined. Unicorn, movements, reward. Get the hot dog. Right? And then what you do is you just randomize this over and over and over again. And then you let it run over and over and over again. Now the training will take a few minutes. So I didn't want to do the training live. I recorded the training and I show you what the result is. And the key point here is I never taught the unicorn how to run there or chase the hot dog. That was completely learned using reinforcement learning. And so here you see how the model, when it iterates, what happens. Right, it first just spins there like nothing. Okay, what do I need to do? Nothing, nothing. Reward is bad, 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 negative reward. Okay, if I go a little bit closer, more reward. I get closer to the hot dog. Ooh, that was a bad one. Right? So it keeps trying like that over and over again. The model suddenly realizes if I circle, there's a higher chance of actually finding the hot dog. And this is really how reinforcement learning works. You keep iterating, nearly got it there, right? Nearly hit the hot dog. And then eventually, the model converts. And it actually manages to get the hot dog every single time within nearly the shortest period. Now, I know this is a bit playful. Maybe you don't do unicorns and hot dogs in your job and in your office. But it's a good example of how reinforcement learning can learn from nothing. It can teach a unicorn to find a hot dog. How cool is that? But you need a simulation environment. You have a simulation environment, then you can build reinforcement learning models. Now, before I leave you off, because in this later on and also this afternoon, you have wonderful sessions across all the topics that I talked about in much more detail, and it will be in Korean, so that'll make it easier for you. I wanted to leave you with a few closing points. The first one, I want you to really think about how can I experiment really quickly? How can I change my design of my architectures so that my developers can quickly iterate on products? How do I build that pipeline that automatically rolls out but rolls back so that I'm not afraid of deploying code out? And how do I build for a global user base? Do I deploy globally? Lots of services that can make it easy for you to do that. Deploy close to the edge. If it's for IoT, there are services for it. Build it on portable web standards whenever you can. And then data. Data is really important, right? Build a cloud data lake, a cost-effective cloud data lake. Make use of the machine learning services that I showed you. Make use of the analytics services that I showed you. It makes it easy for you to build these things very cost-effectively without too much knowledge. And lastly, probably the most important part, focus what's core to your business. Don't build things that don't matter to your business. Racking and stacking server, probably not that important for your business. Building operating systems, building robot operations, building different things, maybe not that important for your business. Focus on what's valued to the business. And the rest, you give it to your cloud computing provider or your service providers that can help you achieve your outcome. That's all I had for today. Please remember to fill out the feedback forms. It really helps us to understand what went well and what not went so well. This will be the feedback for the day, and this will also be put online. And don't forget, if you want to hashtag it, AWS Dev Day Seoul. With that, I thank you very much for your attention. We're going to have a bit of a break, and then there are plenty of sessions to learn some. Thank you.